common protocols. In this nugget, we get to review some of the common services that we've identified in the previous nuggets and focus on what they do, their purpose, and how they operate. It's going to be a lot of fun. It's going to be some review and some new content added in. Let's jump in. So I'm super excited to be here with you as we review the function of common protocols. And a lot of this we've already covered. So this will be a great review on most of the topics. And then we'll kick it up a notch and add a few additional pieces to the mix. So can you remind me, think to yourself, what exactly does HTTP and HTTPS do? What's the function of those application layer protocols? What do they do for us? And if you're saying, well, Keith, HTTP is for web browsing, so this customer right here can go out to a web server like Google, and HTTPS is used for secure web browsing, like to a banking site or a financial institution, you'd be exactly right. That's the function of those two protocols. They're both for web browsing purposes. One's secure, one isn't. Email is these guys right here. So my question for you, SMTP, POP3, and IMAP, which one of those is for getting your mail? For example, the PC right here wants to check in with an email server and wants to pull off its messages that are for that PC, meaning for the user at that PC running an email program. Which of these protocols is going to be used for the client receiving in this direction email, pulling it in? And it is IMAP, and sometimes I think IMAP 4 is the current flavor, and there's also POP3. There's actually both of those protocols are used to retrieve email, and SMTP is to push. So if we need to move email out, meaning send it to a server, or a server on the internet needs to send it to another email server on the internet, it's going to be using SMTP for that. Fantastic. All right, let's do these two next. Telnet and Secure Shell. We already know that they both use TCP at layer 4. We all also know the well-known ports for them. But what do they do? Telnet and SSH. They both do the same functionality. And one does it securely, one does it insecurely. And it is for remote management. So if we want to telnet to a device, so we're sitting here at our computer and we want to get a console access. When I say console access, that's like the command line interface where you have a router prompt where it says I'm R3. There's either a pound symbol or a R3 greater than symbol, and it might be slightly different based on the operating system of your router, but Telnet and SSH both will give us access so we can do it from our computer, run a program that will use the Telnet function or SSH function at the application layer to generate a session. And what's really happening is that if we're using Telnet, we're a Telnet client running the client software for our PC, and the router is acting as a Telnet server. So even though it's a router primarily, for the communication function for Telnet and SSH, it's acting as a server in that capacity. So SSH is secure. We want to use it all the time for remote management instead of using Telnet. Okay, fantastic. We want to move a file. We could go ahead and choose this guy, File Transfer Protocol. So I want to copy a file from a server on the internet to me. I could go ahead and open up an FTP program, or I could open up a browser. So normally we put in our browsers http:// and then the name. But you don't even have to put the HTTP because your browser assumes that if you put a name here like www. There's 3 W's there, google.com, your browser is assuming that you mean HTTP and it'll automatically put it there for you. If you go to a secure website, it may automatically redirect you to HTTPS, so it does it for you as well. And if you wanted to actually go to an FTP server, you could use FTP : whack whack like that, and then the name of the site like ftp.bubba.com, whatever the name of the server is. So this is just what's called a fully qualified domain name. So the ftp.bubba.com server, this says I want to use the FTP protocol, and you can still use your browser. So browsers support more than just HTTP. They support HTTPS, of course, for secure, and they also can support FTP. So when you hit that site, you may have to authenticate, log in, and then you can grab the files you want and copy them. And it would pull them using FTP back to your computer. All right, and remote desktop protocol. The name says it all. You're out here at home. You want to take remote control of a PC, maybe this one right here that's sitting at your company. And as long as the security policy allows it, you can use RDP, connect to this PC, and remote control it. So whatever happens on this screen here shows up on your screen on your computer. It's pretty cool. In that case, this machine is acting as an RDP server, and you're using an RDP client to go ahead and connect. Okay, you're doing great. Oh, one of these UDP ones we talked about. What is the function? Again, that's our goal here. What is the function of these common protocols? So NTP is used to synchronize what? You remember? What is it used to synchronize? NTP, the network time protocol, is used to synchronize time. DHCP is used to hand out IP addresses. So if we have a PC and we don't want to manually assign, for example, what does a PC need? Let's do a little checklist of what a PC needs. It needs an IP address. It needs a default. That's an L, that's a T. Gateway. The default gateway is to the PC is like how I get off the network, meaning how I reach a remote network. So this is a router, which would be a good default gateway for the PC. And we'd also need a DNS IP, meaning the IP address of a DNS server who can resolve names to IP addresses for us. And the easiest way to hand that all out to hundreds of people is to create a DHCP server and then simply have your clients ask for an IP address. And from a previous nugget, we learned that with DHCP, there's 4 packets involved. There's the discover, there's the offer, the request, and the acknowledgement. Let me write that again. DORA. So the client says, I'm looking for a DHCP server. That goes out from the client. The server offers an IP address, says, hey, I've got an IP address here. Would you like it? The client requests the IP address that was offered. How nice. And then the server sends a final acknowledgement saying, you know what? Got your request. And I understand you want that IP address. And I just want to acknowledge to you and anybody else who might be listening that I know you have that address. Please enjoy it. And you can have it for a day. If you want it again, just request a renewal and I'll be happy to renew it for you if I'm up and available. So that's what DHCP does. And DNS, the function of DNS. We don't use IP addresses as humans very much. For example, if I said, hey, come out and visit my website. Sure, Keith, where are you? Well, I'm at 77.25.216.98. That's not as easy to remember as www.cbtnuggets.com. It's easier to remember names than it is for numbers. So on the internet, we have DNS, the domain name system, which allows us to give clients a single IP address of a DNS server. So anytime this client needs to find out what the IP address is of CBT Nuggets or Google or Cisco or anything else, we can simply ask our DNS server saying, hey, Mr. DNS server, trying to reach Google, trying to reach Cisco, can you give me the IP address of this specific server? the DNS server replies, and then now that we have the IP address, we can go ahead and make a forwarding decision. And then one last one here I mentioned was TFTP, the Trivial File Transfer Protocol. It's very much like FTP, except TFTP uses UDP. So let's take a look at something we haven't discussed yet, which is really amazing and really important, and that is the communication between the PC and its default gateway. So I'm going to redraw a couple of things. Sometimes we would often see, for example, a PC here. So let's say this is PC1. I'll label it. And in a network diagram, we might show it connected to a router. That's how we draw an icon for a router. And this router may be shown as connected to another router here. And that router may look like it's connected to the internet. So this topology that I just drew right here, I know it's amazing. It's like, Keith, you have a second career in graphic arts. But this diagram right here really could represent this network up here. Not all the time are we going to see all the pieces. For example, here's physically how all these devices connect to each other. The PC connects to a switch. That switch connects to the router interface. But logically, from a flow perspective, we might see drawings like this without all the physical pieces involved. So I put the icons of the router and the switches. So here's the router, here's the switch. So you could see them. I also wanted to give you a physical view of how the pieces fit together because it's important as a foundation. But I'd like to just take a moment with these guys right here for a moment, and let's talk about this PC going out to the internet. So let's say the goal is to get out to the internet. If this PC is trying to reach now the IP address of this guy is 10.1.0. Let's take a look. Actually, let's back up just a second, and let's take a look and see what that address is on that computer, because you know how to do this. You know how to find out the IP address on a PC. And the way you do it is you go to Start, go to Command Prompt, and then you say what? What is the command to view the IP address? And the command is IP config. So there's our IP address, 10.1.0.51. And it was handed out via DHCP. We could verify that with a ipconfig/all. And sure enough, so there's our IP address 10.1.0.51. It's been handed out via DHCP because there's our DHCP server. There's the DNS server that we're going to use if we ever need to resolve a name to an IP address. And here's our default gateway. So if my computer, which thinks it's on the 10.1.0 network, ever needs to reach anything else, including my DNS server, I'm going to have to forward frames at layer 2 to my actual router. So the flow of traffic would look like this. We would have, and I'll go ahead and I'll use blue, that works. So our flow of traffic, if we took a look at the OSI reference model, the PC here would go ahead and forward at layer 3. The packet would go from PC to DNS. So I'm going to put my layers here actually. So that'd be layers 1, 2, and 3. So the source IP address would be this PC at .51. And if we're going to my DNS server, the destination address would be wherever my DNS server is. Maybe it's out here on this network. Maybe its IP address is 192. Put it out here on a cloud because it's a different network altogether. So let's say it's 192.168.1.1. And that's my DNS server, just for an example. So at layer 3, the IP header would have my source IP address destined to the IP address of the DNS server out on the cloud. At layer 2, what would the addresses be? Now these are the burned in MAC addresses. The burned in or the layer 2 MAC addresses would be from my computer. So whatever my MAC address is here, and what would be the destination MAC address? I'll put PC going to where? what would be the layer 2 destination, layer 2 address inside the frames if my PC was trying to send a packet out to a remote network? And this is the part that a lot of people, I don't know if it's never explained correctly, but it seems like a lot of people struggle with this. Layer 2 addresses, the source and destination, are always going to be local, meaning it's who on your street are you handing this frame to. So if this device right here knew that it had to reach a remote network, at layer 2, it's going to put the layer 2 address of its default gateway. So at layer 2, anytime this PC is going off the network, it's going to put its layer 2 destination as the router. So that's going to be the router every time. Now, if this PC is talking to the printer, it's going to be the destination MAC address of the printer. If this PC is talking to the laptop, the destination is going to be the laptop. But if we're going anywhere off the network, it's going to be this router. So now I have a huge confession to make, and that is, how does this PC learn anybody's MAC address? I mean, how does this PC know what the layer 2 address of the router is? He's going to use it all the time. How does he know? And that's the piece I want to talk with you about right now. And the way it can find out is called ARP. It stands for Address Resolution Protocol. Address Resolution Protocol is how this PC can find out what the layer 2 address is of this router. Let me tell you how it happens. It's fascinating, actually. The PC, first of all, determines that it needs to know layer 2 address of the router. So what it'll do, it will say, I'm going to send a broadcast. I'm going to send an ARP broadcast out to the network. And it sends it down the wire. And what does the switch do when it receives a broadcast? The switch says, I don't have any knowledge of where this layer 2 address lives of all ones, so it's going to forward it out all of the other ports. As it forwards it out all of the other ports, the laptop has to listen to that at layer 2. The printer has to listen to it, and the router listens to it. But as they continue to de-encapsulate and they look at the contents of what's higher up in the stack, higher than just the layer 2 broadcast, they'll all see that it's an ARP request, and they'll see that it's an ARP request looking for the MAC address of the person who owns the IP address of the default gateway. So if this is 10.1.0.1, that's his IP address. In the ARP request, the PC is saying, hey, whoever's got this IP address of 10.1.0.1, I need your layer 2 address, please reply. So the PC says, not me, the printer says, not me, and the router says, holy spamoli, that's me. And it replies. And as it replies, it's going to respond with its layer 2 address. So now the PC knows what the layer 2 address is and now can correctly encapsulate a unicast. A unicast is a fancy way of saying a frame from one device to one other device, and it can send it. Now, that's the theory of ARP. And what I like to do is I like to show you that in action. So let's bring over a couple of devices. Let me clear off this layer right here. And let me add a new one. And let's bring over a router. This is router 1. And I'll just size this up a little bit so we can see it nicely. So this is router 1 right here. And this is the command line interface for router 1. And all we need is a PC. So we'll bring in the PC. And here's the PC. And let me show you real quick what the PC knows about. If there's a new command, this is a new command, I haven't shared it with you yet. It's called, please show me all the layer 2 addresses that you've learned on the network. And it's spelled ARP-A. It's a command that says, show me the ARP entries. Show me all the layer 2 addresses that you know about. And this PC hasn't been talking for a while, so it doesn't know any. But once it learns a layer 2 address of a neighbor on the network, like the router, it will keep it inside of what's called an ARP cache. A cache is like a buffer, a memory space, and it'll keep it for a period of time. It might be 10 minutes. If it's a router, it might be 4 hours, but it'll remember that layer 2 address. So the next time it needs to use it, it doesn't have to go ahead and ask for it again. In the background, I'm going to turn on a protocol trace, and we're going to capture this traffic in action. So I'm going to say start capturing. So that's capturing right now. Also on the router, I'm going to do a little trickery. I'm going to do a debug. Now, debugs are used when you're usually troubleshooting or learning. In a production network, a debug is going to take a lot of extra CPU from the router. So if you are in a production network, you want to be very careful on how you use debug. This is a closed track. It's just you, me, these routers and devices. So it's not a big deal here. It's not going to really bring down any production network. I'm going to do a debug ARP. Now what debug does, it's going to allow us to see all the activity for address resolution protocol that happens on this device. So how do we populate the ARP cache? I'm just simply going to do here's my, this is cool too. Here is my IP address, 10.10.51. There's the IP address of my default gateway, which is my router. So if I just ping, send a ping packet. A ping is a great way to verify basic connectivity. If I send a ping packet to 10.1.0.1, my PC will say, oh no, I don't know the layer 2 address of that. It'll cause him to do an ARP request first. There will be an ARP reply coming back from the router. And then once he knows the layer 2 address, he can then send out his ping request. Ping is where you say, are you there? And a ping reply basically says, yes, I'm here, and you have connectivity to me. So we're going to use that as a tool to verify our connectivity here. So I've got the debug in the background. Let me scroll this over just a little bit, and let's do a ping. Ping to 10.1.0.1. That's the IP address of the router. And if you'll notice, in the background, we have some activity. And you don't need to be an expert at all on, debugs on a specific operating system for a router. However, I want to just point out that what this is saying, hey, I got an ARP, and it was received, and it was a request, and it came from the IP address 10.1.0.51, and the source layer 2 address of that PC was 001B 77123456. The reason that's inside of an ARP is because we don't want to have the router have to do its own ARP for us. So when we ask somebody for their layer 2 address, we also send our layer 2 address so they know. In the ARP request, it was looking for the owner, the person who has this IP address, 10.1.0.1, which happened to be this router, and it was heard that ARP request on FA10, which is this fast Ethernet interface right here. So what do? If you're a good router and you've gotten an ARP request for somebody asking for your layer 2 address based on your IP address, you'd respond. So that's what we did next. ARP sent. It's a reply, not a request now. And the source of the reply is our IP address. We're including our layer 2 address. Our MAC address is the router sending it back. And we're sending it out to 10.1.0.51, which is our PC who asked for it. And we're sending it to the destination layer 2 address of that PC. And we're sending it out fast Ethernet 1/0. So in the background, if we now do an ARP-A on this PC, it says, oh, I know about 10.1.0.1. There's his layer 2 address. And it is. Now the frames that we send to that device are going to go ahead and be addressed appropriately to that, as long as my PC remembers the layer 3 to layer 2 mapping between the logical layer 3 IP address right here and the layer 2 address, which is the MAC address in this case. So the protocol analyzer has been running. Let's take a look at it. So let me move the PC temporarily out of the way so we can see, and I'll lift this command line interface to the router out of the way. Moved it. Heavy. All right. Actually, it's not that heavy. And here's our trace. And the reason I love traces is because it helps reconfirm what we think is happening. A lot of times I'll go on a network and I'll do a protocol analysis. I'll think, wow, what the heck is all this stuff? I wasn't expecting it. And a lot of times it's a problem on the network. So this network right here, just as a heads up, is not a closed track. There are some other protocols that are floating through here. So I sniffed all of this traffic right on this interface, right between the router and the switch. So that's why it says from R1 to switch 1, is because that happens to be where I collected this data. All right, so focusing on the parts that we just discussed, the PC has this layer 2 address. And if we take a look at this source MAC address right here, the PC said, you know what, I need to do an ARP request. I need the layer 2 address of my default gateway because I need to forward frames to him so that he can take those packets at layer 3 and forward those requests out to the internet or wherever we need to send it. In this case, the ping was directly to him. So here's our source layer 2 address, and this is the source address of the PC, and the destination address is all Fs. Now remember, all Fs, that means it's all ones. An F is 4 ones in binary. A binary is just like a light switch. It's either on, a 1, or it's off, a 0. And that broadcast was forwarded to all the devices in this little piece of our network here, including the router. And when the router got it, it sent a reply. So this next frame of data is the reply. This is sourced from the router's layer 2 address going to the actual destination of the PC. In fact, let me just show you real quick. And we looked at this earlier, but I just want to confirm for you what the actual addresses are. So the source address for the actual routers right here, it's CC1E67831111. I carved that in there to make it really easy to recognize. But I just want to make sure that you see that these are the MAC addresses that are involved. So if we go back to the conversation here, if we look at the echo reply, inside this reply message, the ARP reply, if we look at this reply message, it's saying, okay, this is a reply from the router at this IP address. Here's my layer 2 address you were looking for, and I'm sending this to the PC at 10.10.51 to the MAC address of the PC. So the big conversation is a broadcast goes out, everybody listens to it, and the device who has the IP address in question responds with that device's layer 2 address. That's it. And then we have the next protocol here, which is the ping. Now, ICMP, which is being used, is interesting. It's like the workhorse for the internet protocol. So if we take a look at this right here, this protocol stack, sometimes we refer to this as the TCPIP protocol suite. It's a suite of protocols. It's a collection. They use the TCP name from layer 4 and the IP name from layer 3, but it really includes a whole bunch of protocols and application layer services, and there could be new ones that could be added from time to time. If enough people agree and want a new feature or standard, it can be incorporated into this protocol suite. So over here we have the OSI Reference Model right here, and here we have the actual TCPIP protocol suite, which kind of corresponds to that model, which we've talked about in the previous nugget. So the point I wanted to bring up here is that at layer 4, we have protocols like TCP. And TCP is connection oriented, meaning it wants to send acknowledgments and sequence numbering, and because of it, TCP has a lot of overhead. But we use it for applications that require it, like these right here. UDP, on the other hand, has virtually no overhead. All it has is the source port, destination port, and a little thing for checking the integrity of the segment to make sure it didn't get damaged in transit, and that's it. So TCP has tons of overhead, acknowledgement, sequencing, it's reliable, and UDP is unreliable, connectionless, and it also has less overhead, so it's going to be faster for moving data. Also, and I'm going to call it layer 4 because that's what it really looks like, we have something called ICMP. ICMP stands for the Internet Control Message Protocol, right here. ICMP is kind of a partner with IP, and it does a lot of work, meaning if we send a packet on a network and there's some router or some device that can't forward it, it could send us a message back saying, oh, I killed your packet, or I couldn't forward your packet. It's like a behind-the-scenes maintenance protocol. And those would be ICMP message types, or ICMP packets, if you will. So ICMP does have its own protocol number. So if we look at layer 3, at layer 3 we have an IP. So here's IP version 4 being used. And if you look at where it's going to, we're handing this up the protocol stack to ICMP, which is protocol number 1. It literally is protocol number 1. So different protocols at layer 4 have different protocol numbers. We should talk about that for a moment. They're right here, and let me just point them out. So ICMP has a protocol number of 1, and TCP has a protocol number of 6. UDP has a protocol number of 17, and we'll talk about IGMP a little bit later. So why are these important? Why do they even matter? Well, let's say your IP packet and you're carrying payload for somebody. How do you identify inside of the protocol stack who you're handing it up to? And the answer is, in IP, it's going to have an indicator of what the layer 4 or what the next protocol is, what the next layer is. So if this IP packet was carrying TCP, it would say, I'm handing this up to protocol 6. And if it was a IP packet carrying the contents of UDP, at the IP header, it would say, I'm handing this up to protocol number 17. So one other thing I want to make sure you're really clear on is that right here, these are all port numbers. Make sure you make that distinction. These are well-known ports. And at layer 4, we're dealing with protocol numbers. So sometimes people get those confused, or they discuss them, casually as if they're the same. But protocol numbers identify layer 4 protocols, and port numbers identify unique identifiers, if you will, that are commonly used with services. So that's the difference there. One last thing I'd like to share with you is that there's if you and I lined up 100 network engineers and we said, what layer of the OSI reference model does ICMP work at? Probably most of them would say layer 3, even though it distinctly has, its own layer 4 protocol number. So just don't worry about that. Just be aware that a lot of people think about ICMP as a maintenance protocol working at layer 3, but because it does have a protocol number, it goes there. You don't need to start a fist fight with anybody. You don't need to have long arguments, because you could if you wanted to. But the key is that every layer has information of who to hand it up to. For example, the logical link control, its job is to keep track of what layer 3 protocol. There's more than just IP. There could be IPX, there could be AppleTalk, and other layer 3 protocols. So the logical link control specifies who to hand it up to. So if we look at our protocol analyzer, which we will, check this out. In our protocol analyzer, in the layer 2 header, it says, if I open it up, it says hand this up to IP, which happens to be hexadecimal 800. That's the layer 3 number for IP. So in the IP header, it says, okay, who do we hand this up to? Well, the protocol I'm supporting is ICMP. And then if it was UDP, we'd have UDP headers and TCP headers if it was TCP, and they would indicate based on port numbers exactly which application layer service it was for. So everything kind of ties together. So in this discussion, however, our focus was on ARP and also on ICMP. In this ICMP packet, it's a ping request. And the ping request is saying, hey, are you alive? Are you okay? Are you there? And if the device is, and it's willing to reply, it can send an echo reply. And here's the reply coming back. So it's a ping reply. So it's also referred to as an echo reply. And this is just the router responding back saying, yep, I'm alive. And I got your ping request. I'm giving you a ping response. And we're using ICMP, the Internet Control Message Protocol, as the workhorse for that connectivity verification. So another amazing thing that's happened over the last decade is something called Voice over IP. The acronym is spelled VOIP. And Voice over IP is all about taking our existing data network. I mean, we're already routing IP traffic all over the place. Why not move our telephone traffic over IP packets? So we could take a telephone, for example, that plugs into a switch port, and this would be, I'll call it telephone A, and maybe we have another switch over here, another device called telephone B. And if these two devices wanted to go ahead and communicate with each other, the network, the phones would digitize the voice messages into packets. The packets would be forwarded across the network, and it's absolutely amazing. Now, there can't be lots of latency, because if it takes too long to get a packet from here to here and it's not consistent in how they are delivered, it could be choppy as far as a voice call. But it works great if the network's designed to support it. Another feature that we're going to have with voice is something called QoS, quality of service, which may tell the network, you know what, if you ever see the voice traffic, give it precedence, meaning give it the first shot at going through the network, and other traffic like email and stuff, it won't care if it has to wait a few milliseconds. Send the voice traffic first. And that's what QoS is all about. So a couple protocols I want to introduce you to that are used with voice. And one is called the SIP, Session Initiation Protocol. And that's the protocol that can be used by a telephone, so that when somebody dials on that telephone, it can logically connect this phone with another phone so a conversation can happen. And that very likely may be using TCP as its protocol for the actual setup of the call. But actually, after the call is set up, the actual flow of traffic, we don't want to use TCP for the actual streaming of our conversations back and forth because of the overhead. TCP has all that extra overhead that we have to deal with. So instead of using that, they'll use UDP, and there's a special protocol called the Real-Time Transport Protocol, RTP, that's used for the actual carrying of the data, and that uses UDP. So SIP and RTP can both be thought of as application layer services. SIP sets up the connection, uses TCP as a transport layer service, and Real-Time Transport Protocol is used for the delivery, and it's also an application layer service, but it's going to use UDP at layer 4. So those are some concepts or terms that you may hear, and they both relate to voice over IP. So let's do one more new concept, and then we'll do a little review, putting all the pieces together. And one last piece I'd like to share with you is, what if this router, let's take this one right here. say we're managing that router, and we know how to do it too. We're sitting here, we're using either Telnet or SSH to connect to that router so we can see how it's doing. Maybe we want that router to go ahead and report in occasionally. For example, dear Mr. Router, if your CPU gets higher than 80% and you're having a really tough time, let us know. Well, by default, routers don't just phone home and let you know. But what we could use is use another protocol, and a common function for management of our networks is called SNMP. It stands for the Simple Network Management Protocol. And I hope as you're going through this with me, you've got a pen and paper and you're jotting stuff down, because it'll help you remember it. Simple Network Management Protocol. And it really is quite simple. Let me tell you how it works. It's got two pieces. There's a server, also called a manager, and that usually lives on, you could actually run one on your PC. There's just software that runs on your PC. And then what you're going to do on the device you want to manage, it's going to run an agent. And that runs in software. And so most routers and switches support some flavor of SNMP. There's version 1, several flavors of version 2, and there's several flavors and options with version 3. Version 3 is the only one you really want to use, though, because it offers authentication of your managers and it can encrypt the traffic between the manager and the SNMP agent that's running on your router. So here's how it works. You can tell the agent, hey, listen, when you get past 80% utilization, send me a message. And when this guy generates a new message and it goes up to the actual manager, they call it a trap. An SNMP trap. So a trap message is sourced by the router or managed device, and it sends that message up. So you can configure your levels of what you want it to send. The other side of the house is if at the PC that's running the server or the SNMP manager, we can send out requests for information. We can actually on demand say, hey, please tell me what your utilization is on this interface right here. And that's called a get. So we can do a get, also called a read. So it's a read, is basically getting information from the SNMP device. So it's a read or a get. Those are synonymous. They mean effectively the same thing. The other option from the manager is we could actually change data. If we want to shut down an interface using SNMP, we could send a write. So sending a write request, saying I want to shut down this interface, I want to change some parameter, and that's it. So with SNMP of the ability to write from the manager, you can do reads, like getting information, and you can also have a trap that's sourced from the agent without being prompted for it, where it sends that information up to the manager. And that's what SNMP is all about. So let's take a holistic approach to our conversation, and let's bring in the PC. So with the PC, let's do a couple of fun things to generate some of these common network protocols that we've been dealing with. I'm going to go to modify the properties of my interface, my network interface card. Go to properties and go to TCPIP and click on properties. Here it's specifying that I want to use an IP address automatically, which means I want to be a DHCP client. To trigger this whole process, let me go into those properties again, and let me disable this interface and give it a second to settle down. So it's now disabled. And what I want to do in the background, I want to start our capture of all the traffic on the wire right here. So anything that goes between the router and the PC, we're going to capture on this wire right here. So we'll start that capture. It's going, and now we'll simply start up this interface. So we'll go ahead and say enable. All right, and now it's connected. So now that our interface is up and running, let's go ahead and do a real simple browser request. We'll go out to maybe cbtnuggets.com. We'll go to CBT right there in my cache. So I should say my history. So go to cbtnuggets.com, and that used a couple additional protocols as well. And let's go ahead and take a look at, let's logically think together. What protocols between you and I were just used, and then we'll look at the protocol analysis to verify that what we think happened actually did. All right, so I've stopped the capture in the background. Let's move this guy out of the way, and let's talk, the two of us. Let's talk about the protocols that were in use. When the computer disabled its interface right here and re-enabled it, because it was configured to obtain an IP address automatically, I'm thinking the first protocols involved were probably DHCP, Dynamic Host Configuration Protocol. Then, when we opened a browser and we said, I would like to go ahead and communicate with cbtnuggets.com, which is right there, there's their server, hanging off of the internet, one of their servers. Then the next thing we'd have to do is say, well, if we need to go to that server, we need to know the IP address. So the next thing that would have happened was a DNS request. Now that DNS request, unfortunately, the DNS server is not on this local network. So to reach the DNS server, we'd have to go ahead and forward a frame to our router so that our router could forward the packet out to the DNS server. So very likely before DNS, we probably had ARP, Address Resolution Protocol, that was being used by this client to find out the layer 2 address of its default gateway. Then once we had the layer 2 information, we resolved the DNS, then we used HTTP. And by default, if you don't put it in a browser, you put it in a name, that's what it's attempting to use to that server. So we have an HTTP session out to cbtnuggets.com. So that's the theory. Let's bring in the protocol analyzer and take a look at what literally happened. So let the protocol analysis begin. I'm always amazed at what I see when I use a protocol analyzer. I have traffic that I'm expecting, and then there's usually something above and beyond the defaults that I was expecting. And this is the case as well here. So we're going to start from the top of the list. We have some routing protocols. Routing protocols are being used. We talked about this in routing and switching for one router to share information with another router. So we have routing protocols in use. OSPF is an example, you remember, of a link state routing protocol that happens to be running. And then I have my discover. So this discover, DHCP discover, is coming from my client. If we take a look at the source MAC address, there's my source MAC address of my PC, and the destination MAC address is the broadcast. This is my client saying, hey, I need a DHCP server. There happens to be one, so it made an offer. In the offer, it said, I have a beautiful IP address. I think you'll like it. So if we look at the offer details, take a look at this. There's the IP address in the offer that's being offered to this client. And then we have a request where the client is saying, I'll take it, right here. And then we have the acknowledgement from the server. So that's the four, and in that acknowledgement, we have included things such as, here's your default gateway of 10.1.0.1, which happens to be me, says the router. Here's the DNS server you're supposed to use if you ever need to do name resolution. So that's DHCP, the D-O-R-A, Dora the Explorer. That's a good way to remember, though, the actual 4 packets involved in a DHCP. So now that we have the DHCP done, look at this. Gratuitous ARPs. Now, what is ARP? Well, ARP is when you need to find out the layer 2 address of somebody else. Now, what is gratuity? Now, in a restaurant, if we go into a restaurant and we leave a tip, that's gratuity, meaning we don't have to leave a tip, but we did. A gratuitous ARP is when you send out and you advertise, hey, here's my address, when you don't have to. Now, the reason that it's doing this is because it's trying to protect itself against duplicate addresses. You can't have 2 houses on the same street with the same house number, unless they are the same house, but two different houses can't have that same house number. So we're sending out these gratuitous ARPs, and that's, my friend, when if you did have a conflict on your network with two devices, both the screens would pop up a message saying, duplicate address detected, warning, warning, warning. So that's what that is. That's a little extra bonus that we probably weren't expecting. There's some IGMP. IGMP is used for multicast. So this is actually from my computer, and it's basically saying I'm going to join the group 224002, which is a multicast group for routers. We'll save the multicast discussion for another day. But that's what IGMP is. And that's the protocol right here. IGMP at layer 4 is protocol number 2. So if we took a look at it, check it out. So at layer 2, it says hand it up to IP. In the layer 3 header, it says hand it up to IGMP, which is protocol number 2. And then it has whatever the purpose of that management group adding was, which we'll talk about in another discussion on another day. So there's some IGMP traffic. There's some additional non-related traffic that to our discussion. It's got some NetBIOS stuff going on because it is a Windows machine. And let's get down to so NetBIOS, again, more NetBIOS traffic. And now we're going to do our DNS request. This is just before I typed in www.cbtnuggets.com. What happened is my PC said, ooh, cbtnuggets.com, I need the IP address for that. I need to reach and talk to my DNS server who's not on the local network. So it's going to have to use the layer 2 address at layer 2 of the router to get out. He doesn't have it, so that causes the PC to do an ARP request for the router. So here's the ARP request. It's sent from the layer 2 address of the PC to the broadcast address. That would be forwarded by the switch to all other devices on that same VLAN, on that same network. And everybody would listen to it. Everybody would open it up. They would see it's ARP. Everybody would open up and say what he's looking for. And only the router who has the IP address of 10.1.0.1 would then still be interested. Everybody else would say, oh, that was a waste of time. It was a bad book. I didn't need to read it. It's like chapters in a book. Chapter 1, Chapter 2, Chapter 3, OSI Reference Model layers. So the router responds. Here's the reply back. So now the PC knows the layer 2 address of the router. So the next thing that happens is the DNS request. So here's our DNS request from the IP address of the PC. If we look at the layer 3 header, from the IP address of the PC sourced from 10.1.0.53 going to the IP address of our DNS server. That's the IP address of the DNS server we're supposed to use. We were assigned that during the DHCP process. So we forward this packet at layer 2 to our default gateway because he's the only way that we can get off the network. So layer 2 addresses are only good on the same exact little street that you're on. So layer 2 addresses are going to be swapped out here, are used here between the PC and the router. And when the router sends it off to this router, he'll strip off the old layer 2, re-encapsulate a new layer 2, and the next destination layer 2 address will be the actual this router with the source address of this router at layer 2. So the layer 2 addresses change on every hop as a packet is routed. So there's our DNS request, and right here, and here's our DNS response. So for the DNS reply, as we take a look at the details of it at the application layer, we have our initial query, which said we're looking for cbtnuggets.com. Please give us an IPv4 A record, a quad A, 4 A's in a row would be an IPv6 request. And if we take a look at the answers, it says, here is your information. So it looks like we have a couple. There's some load balancing happening. But this address right here, 23.23.235.60 is one of them. and there's another one here. So we have two options, and I think my browser is going to probably choose the first one to go out, and now that it knows the IP address, it can make a unicast layer 3 request for web services to that server. HTTP uses TCP at the transport layer for transport. Here is something called a three-way handshake. In the world of TCP, when a session is going to be started, instead of just starting the devices, think of the King A and King B analogy. Think of the middle managers on both sides. They are going to communicate with each other just to make sure that life is good, and they're going to synchronize with each other, meaning, hey, I'm going to talk to you. Is that okay? Yeah, that's okay. I'll talk to you. And by the way, do you want to talk to me? They call that, in the world of TCP, a three-way handshake. And that's what these first three packets are here. I should say segments at layer 4. This is the PC, my PC, saying to cbtnuggets.com, hey, I'd like to talk with you. This is the server at cbtnuggets saying, yeah, I'm okay. I will acknowledge that. I'm willing to talk to you, and here's my own initial synchronization number for you. And then my PC says, oh, I got your synchronization number. Here's an acknowledgement. And that way, both parties have sent synchronization requests, and they've both got acknowledgements. It didn't get done in 4 packets because this reply packet from the server did the acknowledgement and a synchronization at the same time. So we'll have more discussions on TCP three-way handshakes, which is what this is. But here's the meat of the matter. Once they're all synchronized, then here's our HTTP request. So at the application layer, it's HTTP, Hypertext Transfer Protocol. At layer 4, this is the layer 4 header, the transport layer. Look how busy this is. Oh my gosh, it's so busy. All of this is for the reliability. And this part that I have circled right here, the sequence numbers and acknowledgements, that is not found in UDP. It doesn't use it. So that makes UDP much, much, much faster. But for HTTP, it's set up to use a reliable layer 4 transport, and TCP is used a ton on the internet. You can tell by all these application layer services who use it. So that's the layer 4 header information. That's the 2 cents, if you will, that's added by the middle manager in our King A, King B analogy. We go down to layer 3 of the OSI reference model, the network layer. Here we have the primary information is the source and destination IP addresses. Source being my computer and the destination being that server at cbtnuggets.com. And do you remember where we got that IP address? I mean, how did we know that that address, the ones highlighted, is CBT Nuggets? And the answer is, how did we learn? Yes, DNS, domain name system. It actually, we made a request, we got a reply, and that's how we know. So inside the IP header, the 2 primary elements are the source and destination layer 3 addresses. If we go down, and also take a look at this, is specifying in the layer 3 header what the upper layer protocol is. So inside the layer 3 header, it's specifying, oh, I'm carrying TCP. And inside the TCP, if we take a look at that one more time, it's specifying that it's carrying the traffic for HTTP. So it's all linked together. So if we go down to layer 2, the Ethernet, I want to make sure just you're clear of the fact that whenever we forward frames of data, every time it goes to a router, that data is going to change at layer 2, the source and destination MAC addresses. So in this case, because it's the PC sending it to the router on this little leg of our journey, the source MAC address is the MAC address of this PC. Destination layer 2 address, the MAC address, is the MAC address of the router. How did it get that? Remember? How did it get that address? You're saying ARP, it's ARP, it's ARP. You're exactly right. Or you're a dog that's making ARPing sounds. But ARP, Address Resolution Protocol, indeed, is how this PC learned the layer 2 address here. And it sent the bits on the wire, the router received it, de-encapsulated it, it looked at layer 3, looked at the IP address, and then it made a forwarding decision based on its routing table in the direction of the next hop, so the next hop router could do the same thing and forward it till it gets out to the internet. If we ever ask ourselves, I wonder how many hops we're going over, there's one other cool tool that I'd like to show you, and it's called traceroute, and it uses ICMP, the Internet Control Message Protocol, to do it. Let's bring up our PC one more time, and let's do a traceroute. It's a lot of fun. So we'll go Start, go to Command Prompt, and the syntax for this is TRACERT. It's real. The command is traceroute, but a long time ago, commands couldn't be longer than 8 characters in DOS, and so this is one of those commands that was shortened and never extended on Windows. So traceroute, and I'm going to say -D for don't tell me the actual names of all the routers on the path. And then I'm going to type in www.cbtnuggets.com. And what this is going to do is going to show me each of the routers in the path. So there's a router at 10101. We know who that is. That's my local router. Then I've got another one, 101202, which is my router 2. Then I've got a 24004, which is my ISP router. Let me show you that over here. So I've got my ISP router, which is this guy. And then I have a whole bunch of more routers in the path. I've got one at 1022301, and one here, and one here, and one here, and one here. And then, unfortunately, I have a router at this point who's decided that he's not going to feed me back that information anymore. They're filtering it with some type of a control, like an access control list that says, you know what, we're not going to allow those ICMP echo requests or whatever type of traffic is being generated to make this happen. From a Windows machine, it absolutely is ICMP echo requests. Those are ping requests being sent out. So I'm going to hit Control-C to stop that. And you can see we have lots of routers between where my PC is on my little local network and where the server that we're headed to. So in this nugget, our objective was quite simple. I wanted to review with you the concepts of what these common protocols do. And we've had a good discussion of doing it, including we introduced ARP, Address Resolution Protocol, a couple of protocols used for voice over IP, the Session Initiation Protocol, and the Real-Time Transport Protocol. SIP sets up the connection, and RTP is used to forward the actual packets. And then we have ICMP as well, the Internet Control Message Protocol, which is kind of like housekeeping, if you will, for the TCPIP protocol suite. I hope this has been informative for you, and I'd like to thank you for viewing.